Hi everyone. My name's William Boos, Bill Boos. I'm a professor here in the Department of Geology and Geophysics at Yale, and I guess my job is basically just to introduce Professor Kondo and moderate questions. I'm only going to give you a very short version of what's here on the back of this sheet that you all have. Professor Kondo's been at Todai since 2009. Prior to that, he was at the University of Nagoya for 24 years. And he works on a wide variety of topics in the atmospheric sciences with an emphasis on chemistry and physical processes, doing a fair amount of actually in situ measurements. And he's received numerous awards. Probably many of us here would know the American Geophysical Union, the AGU. He's a fellow of the AGU, as well as several awards from NASA. So without further ado, Professor Kondo.
Thank you for your nice introduction. And actually, this is my first time to visit Yale. And Professor Shun Karato took myself and Professor Abe to this campus, and I was amazed. It's a very nice campus and very good environment for thinking. And also, I would like to thank many people in organizing our visit, and also very nice session here today from Yale University and our university. And then my special thanks to Mike Pagani and Shunichiro Karato and Nobuhiro Hiwatari. He is organizing exchange program in our university. And also, I'm very honored to be here to introduce some of our recent activities in Japan. And I hope that this forum will be a good opportunity in promoting interactions between scientists and at the two universities. So I start with my talk, and this is my contents. And I first make some introduction on radiative energy budget of the atmosphere and probably of the surface. And also I touch on anthropogenic climate change, which is probably well known to the people in this field. And also I go on aerosol effect on climate, and I would stress need for innovative methodology of aerosol studies, and also advances of studies of effect on black carbon. Mainly I talk on black carbon finally, and on climate. Probably you know these figures quite well, but I start with this diagram. The energy of the atmosphere or near the surface is supplied by energy from sun, and about 1/3 of solar energy is reflected back to space, mainly by scattering in the atmosphere, and also direct reflection from the surface. And the rest is absorbed. The rest of energy is absorbed on the surface. And this energy basically is going back to space by infrared radiation at the surface temperature. But significant fraction of this infrared radiation is absorbed by greenhouse gases, and also roughly half of this energy is coming back to the Earth. And this greenhouse effect has a big effect. If there's no greenhouse gases, the surface temperature will be minus 18 degrees Celsius. So ocean is frozen. So it's not good environment for many biological activities. But with the effect of greenhouse gases, temperature, the difference in temperature is huge. We have about 15 degrees Celsius. But this estimate can be relatively easily be done by simple consideration of energy balance. F in is the energy absorbed by the Earth. And Fs is a solar flux in the unit of watt per square meter on average. But only fraction of solar energy is absorbed. A is so-called albedo, which is effective deflection of solar energy. And also Fr is the infrared radiation going back to space. So this term, sigma zero, this term is basically the energy emitted from the surface, but only some fraction of infrared energy is this one. Is going back to space because greenhouse gases absorb a significant portion of infrared energy, and we call it F is a fraction of infrared radiation absorbed by greenhouse gases. And very rather simple radiative transfer calculation can give us some estimate what F will be. And if we assume that F in and F out is balanced, which is does not change in temperature, then we can simply estimate T0, the surface temperature, by this equation. And F is roughly 0.77 and albedo is order of 0.7. And if we put these numbers here, but sigma is a physical constant, Stefan Boltzmann constant, and then we get this temperature. So it's amazingly accurate. And this equation uses only law of black-body radiation. So it's a very robust equation in a sense. And you notice also that surface temperature is controlled only by A and F, which is albedo and absorption by infrared. So it's simple. And Fs is solar flux is probably constant during many centuries. So we can assume that F is constant. So this is the main point. So A and F is only two factors basically controlling the surface temperature on average. And another important physical quantity is radiative forcing. Radiative forcing can be expressed this way. It's a change in energy flux at the top of the atmosphere by changes in many by chemical or physical changes of the Earth. But in this case, if albedo changes, for example, if the Earth's surface or cloud changes, then A may change. But this change in flux can be expressed this way, delta A multiplied by Fs, assuming the temperature is constant. And also, the outgoing flux can be also estimated by change in delta F, which is absorbance. That means a change in concentration of greenhouse gases. And so we call this change as a radiative forcing, which means that change in flux by change in physical conditions between certain period. We usually take change before industrial revolution and after industrial revolution, which is now. And the good, convenient, this radiative forcing is quite convenient in the sense that different chemical and physical processes can be expressed in the same unit, which is energy flux, watt per square meter, which is very convenient. And also a second important point of radiative forcing is that the change in surface temperature can be expressed as the first approximation, lambda multiplied by delta F. Lambda, we usually call it climate sensitivity. And this includes also feedback effect, like change in water vapor concentration, and also albedo by changing ice sheet, for example, or sea ice. It's a bit complicated estimated. But important thing is that delta F radiative forcing is a very critical parameters in predicting change in surface temperature. And F is mainly controlled by change in greenhouse gases, and all of you know rapid increase in CO2 in 100 years, so I'm not going into that part, but I briefly show that how albedo is controlled. We can see the important factors from space. You see that the cloud is very bright, and this suggests that the solar energy is reflected efficiently by clouds. Also, this is pollution over China, and you see hazy aerosol particles. And this also reflect solar sunlight back to space. And another interesting point is that aerosol and the cloud interact with each other. They look different, but they actually interact. This is interesting. Although I'm not going to talk about this relation, but other speakers will talk about on this probably. And then I briefly talk about the effect of aerosol on climate. We have two effects, direct and indirect effect. Direct effect is, like as I show on the photo from space, sulfate or most of the organics are white, which means that it's reflective, and so sunlight is efficiently reflected back to space, and therefore we have less energy absorbed on the surface. So this part first cools, but after that, because of mixing of air, the whole atmosphere will be cooled by existence of light scattering aerosol. But also we have black particles, black carbon typically, but also dust absorbs solar energy. And because of black carbon is black, so it absorbs quite efficiently the solar radiation in visible region. And first, the BC particle is heated, and also by heat conduction, and atmosphere locally is heated. But again, because of mixing, the total atmosphere will be heated. But on the other hand, for a short time period, surface cooling occurs. So this has another aspect of changing in stability of the atmosphere. And second effect, the indirect effect. Aerosol particles generally acts as a nuclei for water vapor condensation, because when air cools, water vapor is supersaturated. Not so large supersaturation, but some supersaturation occurs. And in that case, water vapor condenses on aerosol particles and grows into cloud droplets. And basically, the number of CCN controls the initial number of cloud particles. And if aerosol is larger, number of aerosol is larger, and cloud droplets number becomes larger. And in that case, reflectors of cloud increases. And therefore, aerosol indirectly influence the cooling by clouds. But again, I'm not going into this second effect. Let's all estimate how much aerosol will affect the radiation budget. This is CO2 radiative forcing between 1840 to 2000. This is a bit old data about it, 1.7 watt. And black carbon, this has a larger uncertainty, but it contributes roughly 0.8, probably maybe smaller, 0.5. And light scattering aerosol is minus 1.3, and aerosol indirect effect minus 1. And you see the magnitude of this radiative forcing is relatively big. You see, even as compared with CO2 heating. And this component F, and this part is albedo. And total direct aerosol cooling is of some of these, and it's about minus 0.5 watts. But CO2 gas is quite long-lived and stable and uniform. So we have much less uncertainty as compared to the estimate of radiative forcing by aerosol, because it's short-lived and homogeneous spatially and rapidly changing. And cloud effect is much more uncertain. So we have still large uncertainties in estimating radiative forcing. And still the estimate of radiative forcing in more reliable ways needed in making improved prediction of climate change in future. So here I mainly focus on black carbon. This is because one of the reasons is that this is major effort that we made in recent years. And this is the, I took this figure from recent paper by Bond et al. It's an assessment report on black carbon effect on climate. Black carbon is black, but in fact it's not spherical particle. It's a fractal, has structure made of carbon particles. Roughly the total size is about 1 micrometer or less than 1 micrometer, but it's an aggregate of much smaller spherules with diameters of about 10 or 20 or 30 nanometers. And BC, black carbon, is emitted by incomplete combustion of fossil fuel and biomass, like forest fires. So we have a lot of industrial or human activities going on, and also fires and biofuels also causes BC emissions. And as I mentioned, BC strongly absorbs radiation and heat the atmosphere. And I mentioned this. And so also the black carbon, when transported too far into the Arctic region and the mountain regions and deposited on the snow and ice, it makes these materials dark, and so it tends to melt earlier, and it may contribute to the warming of the Arctic. Well, then I go into more details about microphysical properties of these, and why we need to understand this microphysics. This is the rough estimate of absorption cross-section per unit mass of black carbon for visible range. So you notice that efficiency of solar energy by black carbon is made in small size, very also size dependent. Mostly the about 200 nanometers particles are most efficient, but again, to have good estimate, we need detailed information of the size distribution, and size has to be known by observation, and also model has to include this information. And another important point of BC, and probably more generally in aerosol, is that after emissions during transport of these particles, condensation of oxidized gases like sulfuric acid, oxidized organic species condenses onto black carbon and make coating. Why is it important? Compared with naked black carbon and compared with comparing with coating, it increases light absorption up to factor of 2. We call it lens effect. So effective cross-section becomes larger. And another opposing effect is that it tends to act more effectively as a cloud nuclei. So it under supersaturation, it grows into cloud. The saturation, the reason why it grows is that because of oxidation, it contains oxygen, and oxygen tends to attract water vapor because of hydrogen bond. So it tends to act as a CCN, or collector of water vapor under supersaturation. And after that, if conditions is good, then it is removed by precipitation. So its opposing effect is that coating enhances absorption, but on the other hand, it shortens the lifetime of BC. So it's this effect is rather complicated if we're going to estimate the total effect. So not only for this, but recent years, we need a new concept for improved understanding of aerosol direct effect. Previous aerosol studies were based on bulk properties, typically total mass concentration. But however, as I showed, radiative effect strongly depend on microphysics, especially the number, size, and mixing state. And also aerosol has to be treated as ensemble of individual particles, not single big particles represented by total mass. And to achieve this, we need innovative technologies for measurements. Also, modeling has to be improved greatly. And for this, we spent a lot of efforts in having black hole measurement right. We used laser-induced incandescence. It's a basic design, so-called SP2, which is commercially available, but we made a lot of modification. Where the laser beam is produced by cavity, and aerosol is introduced into laser beam, and black carbon is black, and therefore it absorbs young laser light strongly, and in a very short time, like in microsecond, it heated to about 4,000 degree Kelvin, and therefore it emits black body radiation. We call it incandescence. And fortunately, the peak intensity of this radiation is roughly proportional to the mass of BC. And also, we need estimate the coding, and this is more complicated. I'm not going into detail, but my colleagues made a nice algorithm to derive coding by combining the intensity of signal of incandescence, also light scattering, time-dependent light scattering signal. Simply, BC tends to heat the coding first, and so signal changes, scattering signal changes, but also it emits black body radiation. With this combination, we can estimate the total mass coding BC. And also light scattering part is much easier because it only gives light scattering. So we have basically all information what we need to describe ensemble aerosol by this technique. But we have problem with size, but still basically. An important point of this technology is that we have no interference. Even if BC is coded, we can estimate total mass of BC, which is very different from previous technologies. And for modeling, my colleagues made a lot of effort in describing both size and mixing state, coding thickness of BC. And we made two-dimensional representation of this state. With x-axis aerosol diameter and y-axis mass fraction of BC. And with this representation, changes in number of aerosol and BC and diameters and mixing state can be expressed using based on chemical or representing accurately the physical and chemical processes, and especially condensation and coagulation can be expressed by this framework of the model. And by making instrumentation we developed, we made first mission in East Asia, and this is Japan and this is China. It's behind this figure, but it's a big source of aerosol. And we flew over East China Sea and we went to Korea and back and Yellow Seas. And for this flight made in April 2009, we have 21 flights, and we have a significant amount of data using relatively small airplane. And this is the average mass concentration of BC, blue one is observed. Oh, sorry, I forgot to mention that the modeling framework which we made is a regional scale model. It is not global model. It mainly covers only Asian regions, including India and China. So this is a regional scale modeling. We call it Earth CMAC model, modified version. And this, we made comparison with model calculation along the flight track of the aircraft. So we have at least factor 2 agreement between two model and observation. And so reasonably good agreement. Then we look at the global model. This is our Air Force mean profile. And these are the global models which were used for IPCC AR5. And also this is average, the average for this period. But you see there are a lot of order of magnitude differences between so-called aerocom models. And so at least at this stage, there are a lot of difference between models. And another point is that we can understand that models are different, but we need to understand why models are so different. So we need another parameters with which we can diagnose the performance of models. And wet deposition is an important parameter for controlling the BC concentration in the atmosphere. And we estimated the fraction of black carbon remaining after emissions from China or Asian continent. And this, we call it transport efficiency, again, which is a fraction which escaped from wet deposition, precipitation. And this can be derived by BC and CO correlation, because CO is emitted in the same region as BC, but not removed by precipitation. And you see it in the boundary layer below 2 kilometers, the efficiency, transport efficiency is about close to 1, but it decreases naturally by precipitation, and it reaches about 0.4 in the mid-troposphere. And again, I compared this with Earth model. It's reasonably good. And also just came from Harvard University, and it's slightly underestimated, but it's reasonable. But when we compare with CAMS5 PNNL, which is basically NGA GCM, in the free troposphere, it shows quite large underestimate. So this parameter is very convenient and useful in understanding why models show different features of BC profiles. And now we are discussing with CAM5 people, and they know that they have strong overestimate of precipitation, so they are now running new version of the model. So probably next week we will have new results from this, and after that we hope to summarize our papers. And then we go also into the understanding of how models, regional scale models, represent mixing state, shell and core ratio. And this is again our observations. This is a whole period, and it includes the whole period and whole altitude range, and calculation reasonably represent observations. So the understanding of coding is important in estimating the radiative forcing finally. And this is microphysical part, but we also went into the measurement of radiation itself. There are several stations, so-called AeroNet, which is organized by NASA, and it is deployed over the world. And it includes some stations in China, and in Japan we have different instruments are used which is, I forgot the name, not AeroNet, but Skynet, but similar in principle. And we made use of so-called single scattering albedo, which is the ratio of total extinction, which is caused by scattering and absorption, and also the ratio of scattering. And if we subtract from this single scattering albedo from 1, it also gives a good measure for absorption. The advantage of using this parameter, single scattering albedo, is that it is not directly related to the total mass concentration. So it gives represent the optical properties of BC or aerosol. So it's good measure. And so our regional scale model can also predict single scattering albedo. And this is a map of single scattering, quantum average single scattering albedo. You see the yes. And in China, single scattering albedo is large. This means that more absorptive in nature. And in outflow from China, it's more, oh, sorry, it's reverse. Is it? It's strange. Single scattering albedo is lower here. Is it? I'm a bit confused. Anyway, let's disregard this, but go this thing. Look at this figure. And AeroNet over China, I thought this is correct. Single scattering albedo is lower, and also in the outflow region is a bit higher. And this is observation, and this is modeling. And modeling observation gives some reasonably agreement. Not perfect, but reasonable. I didn't show it here, but if we don't include a proper or predicted mixing state or coding, this correlation doesn't hold anymore. So the coding is really important in understanding absorption here in this region. But this is just starting studies. We have not even completed this paper. It's in preparation by my colleagues. But this is a good point. And so we should really look at the absorption by ground-based measurement like AeroNet. But the problem is that I didn't show problem, but I'll go back to this issue. Next is that probably this is starting point, but emission is important. We have, not we, but some people working emission inventory, they report how much emission is occurring for each grade. And about 90% of BC is emitted from China. Japan and Korea is negligibly small. But the emission limit estimate of emission inventory has about 200% errors, uncertainties. And to constrain the emissions, we have several stations. But for these studies, we have Okinawa Hedo and which is another station, Fukuejima, and mountain region, Happo, 1.8 kilometers. And we now have a long-term record for BC mass concentration. Because of long-term measurement, we developed a so-called Cosmos instrument, which is filter-based instrument, very robust and reliable, with accuracy of 10%. And we have about 3 or more years record. And for this, we made monthly average with regional scale model and observation. Agreement is very good. And for more detailed comparison, we estimate that emission of BC by current inventory is accurate to within 40%. Central values is accurate to within 40%. It's a big difference between 200 and 40%. So ground-based measurement, when made in downstream of the major sources, it gives a good information of emissions like China. Maybe in India, similar studies can be done. Well, we didn't estimate the global BC radiative forcing, but Bond et al. Made it using many global models. And surprisingly, BC radiative forcing is 0.7 watt, which is big. And including direct effect of BC, it goes to 1.1 watts. It's again huge. But of course, there's offsetting effect like organic aerosol and sulfate emitted simultaneously. But going into that, we have to be careful that this estimate was made by constraining model results by observations of radiation, aeronet. And models underestimated factor 3 compared with observation. So model results are multiplied by factor of 3. And why there's factor of 3 difference between models and observations? There are some possibilities. Emission might be wrong, but also absorbance of BC could be underestimated. Or model might have overestimated the wet deposition. So there are still a lot of things we need to investigate in near future. And also another problem is that is ground-based radiation measurement is correct. This is not our responsibility, but this is another problem. But we have to solve these issues in near future. So I made a summary of my presentation. We have established new methodologies or continuing to establish. Aerosol microphysics are critical to improve understanding of aerosol impact on climate. We have evaluated individual key processes by observation and modeling. It is a step-by-step approach. We need this approach. And we developed instruments to measure key parameters and made field observations. And we developed new models to interpret the new data and made detailed comparison with observation in East Asia. And we are making improved estimate of aerosol effect on radiation and climate. So comparison with radiation is first step. And future, we need more detailed studies of aerosol cloud interaction, but we are weak in these modeling efforts. And we are also making observation of aerosol cloud, but because of time, and I didn't mention about observation, but there's strong effect of aerosol on cloud in East Asia. And these aerosols are mainly transported from China, and East Asia is strongly influenced by this effect. Finally, I thank my colleagues, which made a big contribution to these studies, especially Dr. Koike and Takegawa and Moteki and Matsui. And Koike and Matsui is mainly doing modeling works, and these two guys are mainly doing observations. And I thank my Japanese Ministry of Education and Ministry of Environment for continued support of these programs. Thank you very much.
Thank you, Professor Kondo. So we'll take a few questions now.